Good morning, afternoon, evening, middle of the night, everybody. Thank you for coming to this month's COFFIES Seminar. In honor of the Heliophysics Big Year Mental and Physical Health Month, we're actually going to start with a mindfulness exercise led by Dr. Nicole Cabrera. Oh my gosh, I'm already messing up your name and I've known you for decades. Nicole Cabrera Salazar. That's it. So Nicole, just a little background, got her PhD from Georgia State in astronomy back in 2017. She was an immigrant and first generation student and really put in the work to sort of be a representative from her various communities. But unfortunately, I think that the only way to describe her PhD experience was miserable. And she pretty quickly decided to pivot to trying to make other people's experiences in STEM less miserable. She has a lot of experience on various committees, including several for the American Astronomical Society, the Committee on the Status of Minorities in Astronomy, the Oversight Committee. She also started movement consulting, also back in 2017. So this was a response to her own experiences in STEM. And she founded movement in order to help science institutions like COFFIES foster cultures where marginalized people can thrive. They have a lot of different services. COFFIES, like I said, has been consulting with them, including for our mentorship training. So we all love Dr. Nicole. And she is, before our science seminar begins, going to lead us in a mindfulness exercise. So Nicole, take it away.
Thank you, Shay. What a wonderful introduction. I'm so happy to see also some of the folks who were in our mentoring course this past spring. So shout out to y'all. And I believe we're going to be running another one in the spring of 2025. So usually when we do, it's a 13-week mentoring course. And at the beginning and end of every live session, we do a grounding exercise or a mindfulness exercise. Just to set the tone, settle our bodies, and make sure that we're, there's a lot going on in the world and our lives. Some of us are up really, really late right now. So hopefully this exercise will just sort of settle our nervous system. So there's lots of ways to do this, but what I've chosen to go with today is we're doing a rhythmic breathing exercise. And the reason that we do this is because when we breathe deeply through our diaphragm, which makes the belly expand, it activates the vagus nerve, which is part of the central nervous system, and it activates the parasympathetic nervous system, which helps get us out of fight or flight. So it's an exercise that connects us to our bodies in a way that grounds us and makes us feel a little bit more whole. So if you want, you can go ahead and close your eyes. It might be a little bit helpful. And we're going to start by just drawing attention to your breath, whatever's there. So without judgment, without, any kind of qualifiers, just what does your breath feel like? Is it shallow? Is it deep? And then we're just going to notice whatever is there. And as you notice your breath, you can feel into any part of the body where the breath is. So either in your nostrils or in your chest or in your belly, and just follow the breath as it goes in and out of your body. And now what we're going to do is we're going to take a few breaths together. So first, I just want y'all to, we're going to breathe out all the air that's in our lungs. And then we're going to breathe in for a count of 4, hold for 4, and breathe out for 8. And the reason that we do that is that when we breathe in, our heart rate accelerates. And when we breathe out, it slows down. So if the out breath is longer, it's going to bring your heart rate down. Okay, so just a little science for y'all. So let's go ahead and start. So we're gonna just breathe out all the air that's in our lungs. And we're gonna breathe in, 2, 3, 4, hold, 2, 3, 4, and out, 2, 3, 4, 5, 6, 7, 8. In, 2, 3, 4, hold, 2, 3, 4, and out, 2, 3, 4, 5, 6, 7, 8. In, 2, 3, 4, hold, 2, 3, 4, and out, 2, 3, 4, 5, 6, 7, 8. In, 2, 3, 4, hold, 2, 3, 4, and out, 2, 3, 4, 5, 6, 7, 8. In, 2, 3, 4, hold, 2, 3, 4, and out, 2, 3, 4, 5, 6, 7, 8. Now just notice whatever your breath is doing. You can let go of the rhythmic counting. And just notice how your body feels compared to before you started noticing your breath. Hopefully, heart rate has slowed down, feels a little bit more relaxed. And now, whenever you're ready, you can start to wiggle your fingers and toes, open your eyes. And now we're ready to begin. Thanks, everyone.
Thank you.
So much, Nicole. I feel like I at least am more present for this. All right. So next, the feature of today, we have our seminar by Yuto Bekki. So a little background, Dr. Yuto Bekki is a postdoc at Max-Planck-Institute for solar system research. He studied at the University of Tokyo for his bachelor's and master's degrees, and then pursued his PhD at Max-Planck. He's been working with Dr. Robert Cameron and Professor Laurent Guizon. He got his PhD in 2022, continued his research at MPS in solar and stellar interiors. Dr. Bekki's research interests include numerical simulations of magnetohydrodynamic waves in rotating fluids and solar and stellar physics. He's received the Patricia Edwin PhD Thesis Prize from the Solar Physics Division of the European Physical Society, and an honorable mention from the Sun and Heliosphere Division of the International Astronomical Union. So join with me in welcoming Dr. Bekki. Yuto, you are welcome to take it away whenever you're ready.
Yeah. Thank you very much for a very nice introduction. So do you see my screen? Is it?
Yes,
we
we
can
see your.
Okay. Okay, perfect. Today I'll be talking about the Baroclinic instability in the sun's convection zone, which is often overlooked physical process, but we're going to show that it plays a very important role in regulating the differential rotation. So my talk today will be largely based on our recent paper published in Science Advances. So if you're interested in, you can go read for more details. So, okay, now let me, what is?
So we see a blank screen with an Apple like header bar.
Oh, wait. Let me share again. Do you see my presentation slide?
Yeah.
Yeah.
Great. Okay, wait. All right, great.
Yeah.
Okay, so let's get started. So the sun's convection zone is known to rotate differentially. So the equator rotates every 25 days, whereas the polar regions rotate with a period of 35 days or even longer. And this latitudinal velocity shear plays a crucial role in stretching the field lines and amplifying the magnetic fields via the so-called omega effect, one of the most important dynamic processes in the sun. The internal profile of the differential rotation can be very precisely measured by global P-mode helioseismology, as shown in this upper right panel. So, as I said, the equator rotates faster than the poles, and this latitudinal differential rotation extends almost all the way to the base of the convection zone. So the contours of these of the angular velocity contours are not parallel to the rotational axis, but slightly inclined, indicating that the differential rotation doesn't follow the well-known Taylor-Pradman's theorem. And in order to break this Taylor-Pradman's constraint, it has been postulated that the latitudinal entropy difference must exist in the sun's convection zone, so that the Coriolis torque resulting from the non-Taylor-Pradman differential rotation must be balanced by the Baroclinic torque of this latitudinal entropy gradient. This is called thermal wind balance approximation. And using this approximation, you can actually estimate the latitudinal entropy in the sun. So the poles must be slightly hotter than the equator with the corresponding temperature difference of 5 to 10 Kelvin. So as you know, this latitudinal temperature difference is very tiny compared to the million degree background. So it's extremely difficult to measure this latitudinal temperature difference by direct observations. But in this talk, we're gonna argue that we can infer this latitudinal temperature difference with the use of inertial modes. All right, so let's move on to the solar inertial modes stuff. So when you look at the solar surface observation of large-scale velocity, so this is the flow map, longitudinal velocity flow map measured by supergranulation tracking. You can immediately notice that there are spiraling, global scale spiraling flow patterns around the poles, largely consisting of azimuthal order m=1 component with the velocity amplitude of up to 20 to 30 meters per sec. Conventionally, these large-scale flow patterns are thought to be giant convection cells originating from the deep interior. But recently, however, in GISON 2021, we have shown that they are actually inertial modes of oscillation. So let me explain more detail. So in this plot, we show the power spectrum of longitudinal velocity at the surface with fixed azimuthal order m=1 as a function of frequency and latitude. So you can see power concentration at high latitude corresponding to this spiraling flow pattern. The important thing is when you normalize the power at each latitude, you can see the power excess characterized by single frequency at all latitudes. What does it mean? It means that this flow feature represents a global mode of oscillation of the whole convection zone, rather than stochastically excited giant convection cells. If they are giant convection cells, they should follow this differential rotation curve. But this velocity feature is characterized by single frequency. So it's a standing wave of the whole convection zone. And this minus 96 nanoheltz in the co-rotating frame, the Carrington frame, belongs to the inertial frequency range of the sun. So we identify them as inertial modes. And following this method, similar method, we also identify a bunch of solar inertial modes. But these so-called high latitude inertial modes are particularly important because they have the largest velocity amplitude among all the other inertial modes, including, for example, equatorial Rossby waves and so on. All right. Recently, we have carried out a linear eigenmode analysis of the solar inertial modes and show that these high latitude inertial modes are linearly unstable with the presence of latitudinal entropy or temperature gradient. So in the plot on the right, I show the eigenfrequency of the m=1 high latitude mode. So if I don't include latitudinal entropy gradient, the mode is stable with negative growth rate. However, as I increase the latitudinal entropy gradient in the model, the mode becomes more and more unstable. What does it mean? It means this mode is baroclinically unstable. And
hey, Yuto.
Yes.
What? Just quick question. In the thermal wind equation, you get the entropy gradient, but then on the plot, it seems like you're interested in temperature. So how do you actually get the temperature from the entropy?
So this is a kind of numerical experiment. So I give a sine profile for this dsd theta term in the linearized entropy equation, and then simply vary the amplitude.
But I mean, I guess how do you get the delta S in units of entropy into delta temperature? Like, what is the process? Or like, how do you convert from entropy to?
How do I convert from entropy to temperature? Sorry.
Yeah.
He's asking about the linearized equation of state.
And well, yeah, and specifically, you need two. I think you need two, both the entropy and something else like the density.
Yeah. So I use the linearized ideal gas law as an equation of state. So actually, it's described in the supplementary material of our Science Advanced paper.
Okay, I'll check it out.
Yeah. All right. So where are we? So anyway, yeah, this high latitude mode is very strikingly sensitive to the latitudinal entropy gradient or temperature gradient. So only a pole to equator temperature difference of 3 Kelvin, 3 degrees, is enough to make this mode unstable, which is surprising. And when you look at the eigenfunction, the mode eigenfunction, if I don't include this dsd theta term, the mode doesn't show any spiraling pattern around the poles. However, the eigenfunction of the baroclinically unstable mode shows this clear spiraling pattern, just as we observe on the sun. Well, I wonder how many of you are familiar with baroclinic instability. So it is a very important physical process in meteorology, or in the Earth's atmosphere. But I guess most solar physicists are not very familiar with it. So now let me make a short detour to explain what the Baroclinic instability is. So it's a hydrodynamic instability in a rotating stratified fluid accompanied by horizontal temperature gradient. Baroclinic means that the isobaric surfaces are not parallel to the isosteric surfaces. And this is achieved with the presence of horizontal temperature variation or entropy variation. And this baroclinic state is unstable for fluid pulsar exchange in certain direction. And this kind of schematic explanation is often used to explain the baroclinic instability, but in my opinion, it's much too simplified. It doesn't get the essential point of the baroclinic instability. So let me explain in more detail. So suppose you have a gravitationally stratified fluid, and what happens if you introduce the horizontal temperature variation? The hot temperature perturbation means that the local pressure scale height is slightly larger than the surrounding. So the stratification, so this region is less strongly stratified. Whereas if you have a cold temperature perturbation, this region is slightly more strongly stratified. So whenever you introduce horizontal temperature perturbation, this induces the pressure anomalies in the upper and lower layers. The important thing is that in rotating fluid, the pressure anomalies must be accompanied by vortical motions. This is required by geostrophical balance. So if you have a positive pressure perturbation, there needs to be a clockwise vortical motion to balance the pressure gradient force by Coriolis force, and vice versa for negative pressure perturbation. This is so up to here. So it's so this is the prerequisite knowledge to understand the baroclinic instability. So now let's consider a local Cartesian box near the North Pole of the sun. And then, so we have a warm pole and colder equator. So we have a local box with latitude, longitude, and height. And suppose we introduce sinusoidal velocity perturbation in the middle layer, represented by these positive and negative vortices located in turn. So because of the background temperature gradient, this equatorward flow is hotter than the surrounding, and this poleward flow is colder than the surrounding. Since this region is hotter, this induces positive pressure anomaly in the upper layer and negative pressure anomaly in the lower layer. So in the upper and lower layers, this kind of perturbations are induced. The important thing is, so now this region is hotter, so this induces negative pressure anomaly in below. Whereas, so for example, this part is colder, so this also induces a negative pressure anomaly above. So overall, this is a mutually enhancing system with positive feedback. And so this kind of velocity pattern is unstable for a baroclinic instability. So it's an essentially 3D in nature. And one of the most characteristic property of this baroclinically unstable state is that when you look at these positive pressure perturbation vortex tubes, they are inclined, they are tilted in longitude with height. This is the most characteristic feature of the Baroclinic instability, originally found in ED back in 1949. All right, let's get back to the sun. So when you look at the eigenfunction of the high latitude inertial mode with the presence of latitudinal entropy, you can also see this tilted flow pattern, which is the very characteristic feature of the Baroclinic instability. And we have shown in Bekki et al. 2022 that the linear dispersion relation of these baroclinically unstable baroclinically unstable modes can nicely reproduce the observed propagation frequencies of the high latitude inertial modes. So in summary, the linear analysis of the high latitude inertial modes can nicely reproduce the observed eigenfunction, surface eigenfunctions, and the propagation frequencies. But in order to address the mode amplitude, we need to understand the nonlinear saturation process of the mode because they are essentially unstable modes. So to this end, we have carried out a set of 3D nonlinear numerical simulations of the solar large-scale flows. And in order to circumvent the convective conundrum, we adopt the mean field approach, where so that we don't explicitly solve the small-scale convective motions, but their effects, such as convective angular momentum transport process, lambda effect, are parameterized in the model. For the lambda effect, we follow the profile. For the lambda effect, we follow the profile used in Rempel 2005, so that the angular momentum is transported dominantly equatorward to drive the solar-like differential rotation and the single-cell meridional circulation. In our model, the latitudinal entropy variation is generated by meridional flow, radial penetration of meridional flow into a weakly subadiabatic layer at the base of the convection zone. So in this study, in order to control the baroclinic forcing of the system, we vary the subadiabaticity at the base of the convection zone as a free parameter. All right. So now let's does the movie play? Yeah. So so the movie shows the results from 3 representative cases. So from top to bottom, increase the subadiabaticity. So increase the baroclinic forcing. The movie shows the non-axisymmetric component of longitudinal velocity. Differential rotation, entropy perturbation, and the temporal evolution of kinetic energy for different azimuthal orders. When the baroclinicity is weak, wait, sorry. Oops. Sorry. Yep. When the baroclinicity is weak, all the non-axisymmetric modes are stable and they have very low velocity amplitudes, so nothing interesting happens. However, when the baroclinicity is moderate, you can clearly see that the m=1 mode pops up and the spiraling flow pattern can be nicely reproduced at the surface. However, the amplitude of this m=1 mode is not significant enough to affect, to give a direct feedback on the mean state, mean differential rotation. On the other hand,
sorry,
yes.
can I ask one more clarifying question? Sorry, the delta at the base of the zone, it's the entropy gradient or something that you're varying to make it more.
Yeah, it's a positive entropy gradient in the entropy stratification.
But it varies latitude.
So
Or
yeah, so
maybe
yeah, no, in my model we use latitude. It's a latitudinally uniform profile for this weakly subadiabatic layer.
so what makes it baroclinic?
So the trick is if you have a single cell meridional flow, there is a radial penetration at high latitudes and upward meridional flow at the equator. So if you have a radial penetration into a subadiabatic layer, the positive entropy perturbation is generated at high latitudes. And the opposite thing happens at the equator. So as a result, you have a latitudinal entropy variation at the base of the convection zone. And this,
okay, thank you.
Yeah. Any more questions? All right. Yeah. So when the Baroclinic forcing is sufficiently strong, you can see that all the low M modes become unstable and grow in time. And their amplitudes become large enough to give a direct feedback on the differential rotation. So when you look at the differential rotation, so before the instability, differential rotation is very strong, and you have also very strong latitudinal entropy variation. However, when the mode amplitude becomes significant enough, they give a nonlinear feedback, and consequently, the amplitude of latitudinal differential rotation and latitudinal entropy variation are significantly reduced. So, yeah, how does this come? Wait. So before discussing the nonlinear saturation process, let me make just a single comment that our numerical model can very nicely reproduce the observed spiraling pattern at the solar surface. I think this is very convincing. All right, so now
I see Irina raised hand. Irina, do you want to ask a question?
Yes. My question is, what is rotation rate in simulations?
Okay. So for this omega naught, we use the rotation rate of the rigidly rotating core, which is 431 roughly nanohertz. And then but in the statistical stationary state, we have we have the accelerated equator and decelerated poles. So we have sort of like differential rotation profile. So the system rotation rate, omega naught, corresponds to this orange region.
Thank you.
Are there questions on the chat? I cannot.
Yeah, actually, I wanted to ask. It looks like we've heard in many previous works that people explore thermal wind balance as a driver of the meridional flow. But if I'm understanding what you said correctly, it looks like you're introducing a meridional flow to create an entropy gradient. So I wanted to ask, which one of these is more dominant? Does the meridional flow create entropy gradient, or does the entropy gradient create the meridional flow? or do both of
The
them
meridional flow
simultaneously?
creates the meridional flow creates entropy perturbation. So if you have a hotter poles and colder equator, the Baroclinic torque is to induce the meridional flow, which is equatorward at the surface and poleward at the base. This is not what we observe on the sun. We don't know the deeper layer, but so in short, in my opinion, the Baroclinic torque with the hotter pole and colder equator cannot drive the meridional flow which we observe on the sun. Did I make myself clear?
Yeah, thank you.
Okay, so now let me discuss the nonlinear saturation process. So we found that these baroclinically unstable modes have substantial thermal perturbations, as shown here. And these modes actually transport heat equatorward. So on the plot on the right shows the latitudinal enthalpy flux, which is positive in the north and negative in the south, indicating that the thermal energy is transported from pole to the equator. This is to reduce the imposed initial latitudinal entropy gradient to limit a further excitation of Baroclinic modes. This is how they saturate in the nonlinear regime. All right. Then how is the differential rotation reduced? To answer to this question, we look into the angular momentum equation, and the angular momentum flux is decomposed into several terms. The angular momentum flux transported by meridional flow, non-axisymmetric Reynolds stress of the non-axisymmetric modes, prescribed lambda effect, and viscous diffusion. And in this plot, I show the latitudinal angular momentum flux at fixed latitude, at high latitude, like 75 degrees in latitude. And the reduction in the latitudinal differential rotation is represented by this negative black solid curve. It's a pole, which means a poleward, net poleward transport of the angular momentum. And you can clearly see that this is dominantly caused by the red, the poleward angular momentum transport by meridional flow. It is interesting to note that the mode themselves have the Reynolds stress, which transports the angular momentum equatorward. But this is a superficial effect because it's overcompensated by the forward angular momentum transport by meridional flow. So the net effect of the Baroclinic modes is to transport the angular momentum poleward rather than equatorward. So what brings this change in the meridional flow? So when you look at the meridional, the phi component of the vorticity equation, so we can conclude that the change in the meridional flow is caused by the change in the Baroclinic torque. So as the mode amplitude grow, they start to transport heat equatorward to reduce this ds d theta. And this chain reduction in the Baroclinic torque induces additional meridional flow, which is with a stronger poleward flow at the surface. And this is how the angular momentum is transported poleward, and the differential rotation is reduced. This is what we found. So let me illustrate the complicated, so this is already complicated diagram, but let me try to elucidate the complicated interaction between several ingredients. So in 2D models, we already know the interaction between differential rotation, meridional flow, and latitudinal entropy variation. Like differential rotation drives meridional flow by Coriolis force. The meridional flow transports angular momentum to give a feedback on differential rotation. Meridional flow is also driven by latitudinal entropy variation, so that these two guys are in a thermal wind balance. A new addition here in our study is this guy, the baroclinically unstable modes. So these modes are excited by latitudinal entropy variation and then transport heat equatorward to reduce the latitudinal entropy variation. The mode themselves transport angular momentum to affect the differential rotation, but this is way overcompensated by this whole process, this blue curve. Yeah, I understand this is complicated. All right. So we also carried out a systematic parameter survey with varying Baroclinic forcing. So from case 1 to case 10, we increased the Baroclinic forcing. So the plot on the left shows the relation between the amplitude of the Baroclinic mode at m = 1 and the pole to equator temperature difference in the middle convection zone. So initially, as we increase Baroclinic forcing, the latitudinal temperature difference increases and the mode amplitude increases. This makes sense. But when the mode amplitude exceeds some threshold, the modes begin to transport heat equatorward to reduce the latitudinal temperature difference, so that the latitudinal temperature difference drops. All right. The plot on the right shows a relationship between latitudinal differential rotation and pole to equator temperature difference. And we also show the results from 2D axisymmetric simulations where the non-axisymmetric modes are excluded. And you can see that in 2D axisymmetric model, you can increase the amplitude of differential rotation as much as we want. But this can never occur in realistic 3D cases because the modes give feedback, give nonlinear feedback. They transport heat equatorward to limit the pole to equator temperature difference. So that in 3D models, there exists upper bound, the maximum possible value for the latitudinal differential rotation allowed by Baroclinic instability. And according to our parameter survey, we can use the observed amplitude of the m = 1 high latitude mode and the observed latitudinal differential rotation. We can infer that the pole to equator temperature difference in the sun's middle convection zone is around 7 Kelvin. And also interestingly, our simulation, our parameter surveys implies that the sun's differential rotation likely reaches the maximum possible value, the critical regime, which is very interesting, but we don't really know why. All right, so let me pick up the case which best fits the observation. Here's a comparison. So our numerical model can very nicely reproduce the observed properties of these high latitude modes, like the velocity concentration at high latitude and the power excess at single frequency at all latitudes when normalized, the dispersion relation, and the surface eigenfunctions at azimuthal orders m1, 2, 3. So lastly, let me also make some comments on other interesting properties of the baroclinically unstable modes. So first, we found that the m=1 mode particular has a flow which goes across the poles. So this is the extracted eigenfunction of latitudinal velocity. The latitudinal velocity keeps having non-zero value towards the pole. And this is m=1 mode. So across the poles, 180 degrees apart, there is an exact negative value here because it's m=1. So there is a polar crossing flow, which is much easily visualized in this velocity field plot seen from the North Pole. There is a flow which goes across the pole. The existence of this polar crossing flow has been known for decades, first reported by Uri 1993 and 2001. But to my knowledge, there's been no theoretical explanation for this observation. So our model provides theoretical explanation that this can be explained by m=1 component of the baroclinically unstable mode. Another interesting feature is property of the baroclinic unstable mode is these modes have a substantial kinetic helicity around the poles, which is dominantly negative in the north and positive in the south. Positive in the south. This might have some impact on a spatial distribution of the turbulent alpha effect, and it can affect some dynamo properties in the sun's convection zone. All right. Okay. So let me summarize my talk. So the sun's differential rotation deviates from the Taylor-Prodman, and there's been postulated that a very tiny latitudinal temperature difference must exist in the sun's convection zone, but which is extremely difficult to measure. Recently discovered inertial modes, in particular, the high latitude inertial modes, can be used to infer this latitudinal temperature difference because they are baroclinically unstable and super sensitive to a very small difference, a very small pole to equator temperature difference. So in this talk, in this study, we carried out a series of nonlinear simulations, and we show that these baroclinically unstable inertial modes, so first they saturate by transporting heat equatorward and limiting the latitudinal temperature difference. We can use the observed amplitude of the high latitude inertial modes to infer that in the middle convection zone, the pole to equator temperature difference is around 7 Kelvin. And we also show that the baroclinically unstable modes play a significant role in controlling the latitudinal differential rotation. So our study emphasized the importance of baroclinic instability. So baroclinic instability, as I said in the very beginning, is often overlooked process, but this must be properly taken into account in modeling the differential rotation of the sun and stars. Do I still have some time?
Yeah, sure.
Yeah. Okay.
10
so
to 15 minutes left. Yeah. 10
right,
to
great.
15. Yeah.
Great. So so up to now, all the studies are pure hydrodynamic, and I can easily imagine that some of you might ask about magnetic effects. So let me make a short comment on this in advance. So in principle, we think that the magnetic fields has a suppressing effect on Baroclinic instability. So this is a simple numerical experiment which I insert the toroidal field into the simulation to see what happens. So as soon as I insert the magnetic fields, wait. Up. Yeah. So initially there is a high latitude modes, but as soon as I insert the magnetic field, the high latitude modes are strongly suppressed. It's gone. But as time passes, and then when the magnetic energy becomes, when the magnetic energy decays sufficiently, the high latitude modes are retrieved. And this also affects and when the magnetic fields, when the baroclinic modes are suppressed by magnetic field, the latitudinal equatorial heat transport is also suppressed. So during this period, the latitudinal entropy difference is enhanced and the differential rotation is enhanced. This is very interesting thing to note that. And we also show that this suppression effect, it doesn't care whether the magnetic fields are colloidal or toroidal. It doesn't care. And in the dynamo simulation, because of this suppressing effect, we show that the amplitude of this M=1 Baroclinic high latitude mode oscillates in the course of the solar cycle. Let me play the movie again. So this is the sunspot number proxy, and this is the amplitude of the M=1 high latitude mode. So there's a clear connection between these two. And actually, a similar thing has been observed. So the left is my simulation, the right is observation. So it seems like the observation is very noisy, but it seems like the amplitude of this high latitude inertial mode seem to somewhat correlated with the solar cycle. And this can be nicely explained in our model. So yeah, so in summary, so this baroclinic instability stuff is very interesting, even in pure hydrodynamic, but it's even more interesting in in the MHD regime. Yeah, so that's all for today. So thank you very much for your listening.
All right, let's all thank Yuto. I realize I'm clapping and you can't see me. All right, we can open it up. We have a few minutes for questions. There's been some lively discussion in the chat. I'm not sure where to even start there. But I see that Rajaguru has a question thrown in there. So let's start with Paul.
Yeah. Yes, okay. There is also other hands raised. Maybe I will just go first.
Sure, go for it.
Yeah, so I asked the question, I think Robert has answered that, but I would, I would state the question again. So in this model where you said that there's a complicated balance between thermal wind, the meridional circulation driven by differential rotation, and the baroclinic instability, is there a possibility to have more than one cell in depth for meridional circulation in this model?
Yeah, that's a very good point. In fact, our numerical model relies on the entropy generation mechanism on the single cell meridional flow. So it would be, yeah. So yeah, it would be it would be a future work to see what happens if the meridional flow is the other, the other form. Yeah.
All right. Okay. Thank you.
Thank you.
All right, yeah, and there's a few hands raised. The first one I see actually is Sushant.
Hi, Yuto. Very nice talk and very interesting work. I just wanted to say the fact that you see the sun maintains or tries to maintain the maximum latitudinal shear in rotation is something I observed in my PhD thesis. I'll send a link in the chat. We analyzed global helioseismic inversions on differential rotation with like 6 different data sets. And in all of those, we find that we all know that the mean differential rotation profile is not consistent across solar cycles. But across the past 2 solar cycles, what is consistent is that the sun tries to relax down to a state of maximum latitudinal shear in rotation. And I also didn't know why that was, but it seems like from your analysis, it could be because of the baroclinic torques maintaining that state.
Yeah, that's interesting. Yeah, could be.
That sounds like a deeper conversation to be had.
Yeah, but thank you very much for the comment. I will take your comment. Yeah.
Sasha, I see you next.
Oh, thank you. Thank you for a very interesting presentation. I have 2 questions about your model. Your model includes lambda effect. So
Yes.
differential rotation is actually generated by the lambda effect, not by the Baroclinic instability. So what relative role of this Baroclinic instability and lambda effect in your model?
So we think naively that this lambda effect represents the small scale convective motions, whereas this baroclinic modes, the Reynolds stress of the baroclinic modes occur at much larger scales. It's only m less than 5. But yeah, in principle, they should act as a combined effect. So
okay.
Yeah.
My second question is that perhaps we don't know latitudinal entropy gradient, but radial entropy gradient is measured very, very well by helioseismology. And if you include in your equations, you find that convective instability is dominant on various scales, including large scale, like interpretation by Hathaway of this. So what would be the role of this large scale convective instability compared to this baroclinic?
Yeah, that's
or shear.
Yeah, that's a very interesting, important point. So in my model, actually, this supra-adiabaticity is said to be 0 in the bulk of the convection zone to suppress the convective instability. But we are also working on analyzing the baroclinic instability in the convective, in the rotating convection simulations. But in this mean field model, if I use very strongly supraadiabatic profile for delta, it's really hard to control the system.
Okay, thank you.
Thank you.
Okay, Gustavo, you're up.
Hi, thank you for the very, very nice, interesting talk.
Thank you.
My question is, if you think on Earth, this baroclinic instability happens just above the tropics, It appears because on Earth it needs to be a transfer of heat towards the poles. Because Earth absorbs at lower latitudes, and then for Earth to radiate more homogeneously, heat is transported towards the poles. So everything is about heat transport. So what could be the reason why in the sun you need to develop this instability transporting heat towards the equator?
What? So sorry, what was the last question? Sorry, I just missed it.
So on Earth you need to transport heat towards the pole. Why in the sun do you need this instability transporting heat towards the equator?
Why? Okay. So my short answer is we don't know because in this study we don't aim to address the origin of this latitudinal entropy variation. We just give it. So we start with assuming that the poles are hotter than the equator.
So kind of assuming that there is an non-isotropic transport of heat from the nucleus of the sun towards the exterior, right?
In this in our Meteor model, yes. But there are many rotating magnetoconvection simulations also show that without any trick, the poles are heated compared to the equator because of the rotationally constraint, the not anisotropic heat transport by rotationally constrained convection. So I think that explains to some extent.
Okay, thank you.
All right. Sorry, Shay has to run for another meeting, but the next hand raised I can see is from Lauren.
Yeah, hey, thanks. This is really interesting stuff. I have a million questions about thermodynamics, but I don't want to derail anything. I think maybe Robert and I need to read the paperwork carefully and figure that out offline. I want to be annoying though. I want to make one comment, which is that I think you found a mechanism of stopping the poleward heat transport once it gets to be too strong. And I actually think there's some really interesting synergy here. So I want to see if we can talk more about this offline, because a few years ago, me, Brad, and Yuri basically wrote a paper getting at Gustavo's point, I think, which is that if you have Taylor columns, they naturally transport heat poleward, and this would drive the thermal wind, but then we didn't know what would provide an equatorward transport. And so I feel like we've looked at basically opposite ends of the problem. I don't know, I might be reaching, but it would be great to chat further about this, because I feel like this is like two pieces to this.
Yeah.
And I guess my question is about the equatorward heat transport. It makes sense intuitively that these Baroclinic modes should seek to stabilize, but what is it about them that actually transports the heat? Is it like the spiraling pattern? Is there any intuitive way to see, like, from the polar spirally pattern that these things are transported? I guess that's my question.
So sorry, it was lost at last.
Yeah, sorry. Like in Taylor columns, they naturally transport angular momentum outward. They're spirally. Maybe I'm just thinking of spirals. But can you what is it? Is it the correlation of those spirals that's actually creating the heat transport? How does heat transport go equatorly?
I don't have a concrete answer to that question, but I don't think it has anything to do with the equatorial tidal columns. Everything happens inside the tangential cylinder in these simulations.
Oh, sorry. I just meant, no, I wasn't thinking that the Taylor columns did the heat transport. I'm just, is it a Reynolds stress?
Okay,
like
sorry.
the non-axisymmetric part of the spiral that's, I'm just confused what term is actually transporting heat in your models?
In my model, so it's
Yeah.
It's a longitudinal mean of the non-axisymmetric latitudinal. It's the non-axisymmetric latitudinal velocity and entropy perturbation. So basically, yeah. So it's a
okay, yeah, okay.
So non-axisymmetric components of the meridional flow.
No, meridional flow is defined as axisymmetric. The in my model, the non-axisymmetric component all the non-axisymmetric you can think of all the non-axisymmetric components are modes origin. We actually have a very small random noise in the background, but the modes are dominant. And there's no convection, so.
Okay. Sorry, in the interest of time, we should move to Keiji.
Hi, yeah, thank you, Rick-san. I have one question about it's something like the curiosity rather than scientific. What if you give the longitudinal, entropy gradient instead of latitudinal? Is there any difference? For example, can you create something like the active longitude or something, magnetic activity or something like that? It's just a curiosity. Yeah, thank you.
Yeah, I've never thought of. Yeah, that would be interesting. I've never thought about that, but yeah, in principle, I mean, technically speaking, it's possible to do that in the model, in my model. So yeah, that would be interesting too. Yeah.
Yeah. Thank you. Please try. Thank you.
Yeah. Thank you.
All right, last question, Gustavo.
Yeah, so it's very nice that you are trying with magnetic fields, what is the effect of magnetic fields, but I suppose that the amplitude of the mode that you are seeing and compared with the observations can impose some upper limit for the amplitude of the magnetic field?
Yeah, could be. Yeah, that's a very interesting point. Yes. Yeah, could be. Yeah, that would be very interesting thing to do. Yeah, next. Yeah, I agree.
All right.
Yeah, thank you for the comment. Yeah.
Well, we're about 10 minutes over time. Please join me in thanking Yuto for an excellently given seminar. We'll see you again at the
Thank you
next.
very much.
Yuto, do you want me to save the chat and send it to you?
Yeah, I don't catch up what's going on in the chat. So yeah, that would be very helpful. Yeah, thanks.
I'll send it.
Yeah, thanks.
Thanks, Yuto. Nice talk.
Thank you. See you.
Thank you. Bye.
Thank you.
Yeah, bye.